So once again, a very good afternoon, everyone. This is the second session of Online Gate Training Program 2022. A lecturer on fundamentals of solid mechanics required for cracking problems will be delivered by Dr. Umesha P K, Department of Civil Engineering. I welcome you to the session, sir.
Thank you. Thank
Dr.
you,
Umesha
Girish.
P K is professor in Department of Civil Engineering for last 3 years after retirement from CSIR-Structural Engineering Research Center, Chennai. He is actively involved in teaching, research and consultancy in structural engineering. He will be speaking on fundamentals of solid mechanics required for cracking problems related to the gate examination. A very warm welcome to you, sir. I will, with this, I will request Umesha sir to kindly take over the session. Thank you, sir.
Thank you, Professor Girish. Good evening to everyone. So today I'm going to talk on solid mechanics. So which is going to be one of the chapter in GATE to crack the so many questions in related to solid mechanics. I'm going to explain in few hours. This is the first lecture. So today I'm interested. These are the some of the syllabus of solid mechanics. So solid mechanics, it will cover bending moment, shear force in statically determined beams, simple stress strain and their relationship, simple bending theory, flexural and shear stresses, shear center, uniform torsion, transformation of stress, buckling of column, combined and direct bending stresses. So these are the topics to be covered under the solid mechanics. Today I'm going to talk on moment and bending moment and shear force that is essentially required for everyone in structural civil engineering. So today I'm going to talk on what is a moment. So different types of beams you might have seen, that is simply supported beam, have overhanging beam, and also cantilever beam, etc. So if we see, so on other type, that is all, these are all the determined beams. Other types will be indeterminate beams, that is fixed beam, continuous beam, propped cantilever beams, etc. So here, what is moment? Moment, it is the product of force and perpendicular distance between the action of force and the point about which the moment is required to be calculated. That is the, I think all you know in civil engineering what is moment and all. It is clearly explained here. So what is bending moment? So bending moment, it is the moment which causes the bending effect on the beam is called the bending moment. It is generally denoted by M or BM. So we'll see what are the different types of structures. Okay, just 1 minute. So if it's so in civil engineering, if you see, so what is this? This is called. So it will be simply supported beam. It will be there. So it will be having the one hinged support and one roller support. So it will be having this one. So what is the other one? It will be having a overhanging beam. So a cantilever beam, it will be like this. So it will be having the cantilever beam, and another one overhanging beam. What is overhanging beam? So it will be having the support in the middle. So it will be overhanged on both sides. So it will be having a load either this side or this side, cantilever on other side, both the side. It's called overhanging beams. These are all the determined structures. On the other hand, indeterminate structures, it will be fixed beam. So you will be knowing the fixed beam. Both will be having the fixity, and another one continuous beam will be there. So it will be supported in different things. So either simply supported or this one, and continuously it will be supported. It is a continuous beam. So another one, it is called a propped cantilever. you may be knowing the proper cantilever. So one hand will be fixed and another hand will be having the support. So it will be having the proper cantilever, either overhang will be there or without also overhang there. So these are the different types of determined and indeterminate structures. So what are the sign conventions for the bending moment? So mainly bending moment. So if you see here, so moment is considered as the sagging moment. So that means you will be having the concavity, that is the curvature having the concavity at the bottom of the figure, that is bottom of the surface, that is shown in the figure like this here you see. So sagging moment is considered as a positive bending moment. So for example, it will be having the beam, so it will be having the either simply supported or fixed beam, it will be having support. So if you have a load here, so what will happen? It tries to bend like this. So it will be having the tension members at the bottom. So concavity will be at the bottom. So it will be having the concavity here at bottom. So this type of bending moment is called sagging moment of bending moment. It is considered as positive bending moment. So on the other hand, so if we have a concavity, that is a similarly bending moment is considered as a hogging bending moment if it tends to bend the beam in the curvature having the concavity at the top. So as shown here, so hogging moment is considered as the negative moment. So for example, in the same simply supported beam, for example, you'll be having the simply supported beam will be there. So you've seen the load acting from the top. So instead of acting the top from the bottom, that is soil pressure or whatever it may be, so it will be having the pressure from the bottom. Then it tries to bend like this. Then it will be having the tension members at the top. So it will be there here. So similarly, because of this one, the hogging moment will be having. So moment will be there here. This will be having its side, and it will be having the pushing upward. So it will be hogging bend moment. So you'll be interested to know how we will be having the sagging as well as hogging movement. So sagging is considered as positive movement, and hogging is considered as negative movement. So sign conventions for the shear force. So what are the shear force you'll be having? So if you consider a beam, so it will be having the beam. So it is supported as simply supported with hinge support and roller support. So load, so it will be having the reaction here, and whatever load acting on this one beam. So if we consider a section at any point, for example, it will be considered section at this point. So whatever the forces acting left side of this one, so if it is acting upward, it is considered as a positive. Similarly, if downward, it will be negative. So if it is from the section, if we consider right side, if it is acting downward, it will be positive, and upward it will be negative. So that is considered as here positive shear force. Similarly, you can see here. So what I told similarly here, if it is acting downward it will be negative, and upward it will be negative. So negative. This is negative shear force. So shear force will be having. So from the section you take left side, whatever it is acting upward, it will be positive, and if it is acting downward, it will be negative. So that sign convention very important to remember. So how to write the shear force diagram and bending moment diagram. So shear force diagram, for example, the diagram shows the variation of shear force along the length of the beam is called shear force diagram. Okay, that is called SFD. So similarly, if it is moment it's acting which shows the variation of bending moment along the length of the beam is called bending moment diagram. That is called BMT. Okay, so we are interested to know how to calculate the shear force and bending moment and to draw them. So if you draw in schematically, I am using the beam length and other things. It's called shear force diagram as well as bending moment diagram. So what is the point of contact flexure? So it is the point on which the bending moment diagram where the bending moment changes its sign from positive to negative or negative to positive. So that's called the point of contact flexure. So where you can see point of contact flexure, for example, if you draw the bending moment diagram, so you'll be having the support, you'll be changing the its sign. So it will be having the positive here and negative here. So changing the point from positive to negative or negative to positive. So this is called point of inflection or point of contact flexure. Okay. So we should know what is the relation between this load, shear force, and bending moment. First of all, if you take a beam, so it will be having an arbitrarily load like this. So you'll be having the support at the hinge support and the roller support. So okay, so it will be consider section XX and X1. So at a distance dx. So what will happen? See, this is a simply support beam subjected to general type of loading. So consider the differential element, that is called a differential element dx. So in between the two sections xx and x1, x dash, x dash. So if you see here, so what are the forces acting on the right side as well as left side? So if you take the left side, it will be having the shear force V. Shear force V, it will be acting downward, and it will be having the moment. So since it is a simply supported beam, so it will be having the sagging moment. So that's why it will be having the sagging moment here and also here. And we have the shear force acting downward and up, and the differential element upward. So if we take the free body diagram, so this will be having V, this will be V plus dV. So differential for the differential length, V plus dV will be there. Similarly, if we consider M here, it will be having M plus dm. So this is the free body diagram of that one. So so now we will take the moment about this point. For example, if we take a moment, so what are the forces acting, vertical forces, the downward forces acting at this point? That will become zero. So now we will be having this shear force will be there, and this arbitrary load, it will also acting downward, that also acting downward. So you'll be having the plus these moments, these two moments will be there. So we consider this one anti-clockwise negative. So taking minus m, and clockwise moment will be positive, m plus dm will be there. And so similarly, this shear force acting downward at a distance dx. So it will be having the anti-clockwise moment. So it will be negative here. So v into dx. So similarly, what we have here, the arbitrary load W kilonewton per meter, that is per unit length, it will be there. So take that one W into dx. This is the load acting at its centroid at a distance of dx by 2. So if you take all the things, if you simplify that one, what will happen? Just see here. So neglecting the higher order, this is a dx into dx. It is where dx itself, it's a small value. Square up that one, it will become again small value. So hence neglecting this term, and we will be getting a m it cancel, and remaining will be if you send to other x, v into dx is equal to dm. So similar, what we can say, v relation will be, so v is equal to dm divided by dx. So that means, so shear force will be equivalent to the first derivative of moment, first derivative of the moments. Okay, so that is very important. The relation for shear force, it will be first derivative of the moment. So with respect to the distance along the x-axis. So another thing, if you take a beam, so you will be having the x-axis in the here, x-axis will be there, and it will be having a vertical axis, so y, and shear force axis. So whatever beam will be there, that will be x-axis and upward. So in the left side up end, it will be Vx will be positive. So similarly, if we take downward, so this is x-axis, and moment will be acting upward. It will be, if you want to draw the bending moment diagram, it will be positive like this. You have to consider. So we'll go to next. So next relation. So similarly, if you take the free body diagram, same free body diagram, take the that is the sigma y. What are the forces acting downward, upward? If you take the summation of that one, that is as you know, that is three conditions: sigma m is equal to 0, sigma v is equal to 0, sigma h is equal to 0. So now we are going to take the free body diagram of this differential element. So sigma y, that is fy. What are the forces acting in y direction? Equal to 0. If we take, then what will happen? That is v will be acting downward. So that is the shear force here. And this V plus dV will be acting upward, that is positive. And this side, the load acting here, that is a W into dx, it's also acting downward. So these two are negative and this will be positive. So we are not considering the moment. This is only sigma Fy is equal to 0, only forces along the y direction. So if you simplify that one, so you will be getting dV is equal to W into dx. So what is the relation? So W, that is what is the load, will be derivative of the shear force. So load is equal to derivative of the force. What is the shear force will be derivative of the moment. What you've seen in the previous slide, that is the derivative of the moment. Now, if you see the what is the variation of shear force and bending moment, so let us see how it will be for different bound condition. So variation of shear force and bending moment for various standard loads as shown in the table. For example, here if you say what is the type of load will be, so between the point loads or no load region, or uniformly distributed load will be there. So this is the one, or uniformly varying load will be there. So how it will be there? How it look like in a shear force diagram or bending moment diagram? See, for the shear force diagram, if it is point load from point to point, so it will be having horizontal load, horizontal line only. Whereas bending moment, it will be inclined line. So uniformly distributed load, it will shear force itself inclined line. Then the moment will be 2-degree curvature, that is a parabola. So if we have uniformly varying load, that is if we have the uniformly varying load, that 2-degree curve itself, it will be parabola here for shear force, and bending moment will be cubic equation. So you can see here, so cubic equation, if we differentiate, you will get the parabola. Similarly, parabola, if we differentiate, you will get the line, inclined line. Similarly, inclined, that will be just horizontal, it will be there. So how it will be there, let us see that. For example, so we'll be having the beam. So you have only load. So how it look like your shear force diagram? So what is the shear force here? So shear force will be from here. It will be acting downward. So it will be positive here, and it will be constant throughout, and it will be coming up. This is the shear force diagram. So it will be full straight line from here to here. So if you take, if you take another one, so if you have a simply supported beam with the subjected to a uniformly varying load or a distance, so it will be acting here. Then how it will be, your bending moment diagram will be, so we have the shear force diagram. So here upward, and whatever the load, it will come here, down it will go, and it will come like this, and this is the straight line. So from point load to point load, whatever it may be, it will be only straight line. So whereas in the bending moment diagram, how it will be bending moment diagram, so if you have bending moment like this, it will come. Okay, sorry, that is figure, it will not clear, so it will be like this. So okay, so similarly, whatever you have seen in the previously, So if you have a all so if so you have seen that one, it will be a point to point, it will horizontal line, and your moment will be in inclined line. So if you have a uniformly distributed load, so uniformly distributed load, how it will be, just you will see that one. So uniformly distributed load. So for example, if you have a simply supported beam, it will be subjected to UDL, and it is support having the this one here support and here roller support, and reaction will be there. So your what is your this one shear force diagram will be, so it will be having like this inclined line, whereas your bending moment diagram will be, so once if it's inclined line, your bending moment diagram, you will be having the curvature like this. So it will be positive, this also positive, and this is negative. So shear, this is the shear force diagram, and this is bending moment diagram. Okay. So if similarly, what will happen if you have a uniformly varying load? For example, uniformly varying load for a cantilever beam. So it will be there. Okay. So it will be having the load like this, uniformly varying load. So then how it will be, this is a fixed end here. Then how it will be your variation of your shear force. Shear force will be having the curvature like this. Okay. Then similarly, the bending moment, if it is parabola means it will be cubic equation will be there. So, okay. So that is the one. So next we will go to, so some examples you will take. So for example, now we will be take some example. So some examples of a cantilever beam you will take. So how it will, so for example, you take a cantilever beam, so it will be subjected to load here P. So what is the P will be there? This is the length L. So this is a cantilever fixed at this point. Then what is a Vx? What is the shear force will be? So at a distance, if you take at a distance x from here, so Vx is equal to, so it's P is a constant here. It's acting from, if you take the section left side, it is the negative side. So minus P will be there. So x will be variation if we go from 0, x is equal to, this is the length x from here to here. So x is equal to from here. So when at x is equal to 0, what will happen? Vx is equal to P, it will be there. So x is equal to L means Vx is equal to that also minus P. So throughout the length, the shear force diagram will be, so if we have it like this, so it will be coming down here, and it will be constant this one, and it will go up. So this will be P value will be there. So throughout the length, this will be P value. So if you take what will happen if you so if you have a, so what is a bending moment? Bending moment mx is equal to P into x. P into x, it will be there. So at x is equal to 0, what will happen? mx is equal to 0. At x is equal to L, mx is equal to, so P into L. So here it is also negative sign will be there. So minus P into L will be there. Okay. So how it will be our bending moment diagram? So it will be there. So 0 here, and it will be coming inclined line here. Okay. So similarly, we will take another one. So there is this value. So this value will be PL. So this is negative. So we'll take another example with the UDL. Similarly, just it is a fundamental required. So if you understand this one once, so it will be very easy. So we'll take up another example with the UDL. So if you take a cantilever, same beam will be there. So it will be subjected with a UDL. Say this is a UDL having a W per unit length. So what is the shear force here? Unit length will be there. So bending moment. So what is the shear force here? So if we calculate the shear force, so what is the shear force? Shear force of Vx is equal to, so at a distance x from the edge. So this is from the edge, x is equal to from distance edge. So it will be having W into x, W into x. So W measuring from here, total length will be L. So yeah, at x is equal to 0, what is the Vx? Vx is equal to also, we will be having 0. So similarly, so at x is equal, what x is equal to L? So yeah, at x is equal to L, what will happen? So Vx is equal to, this is also, we have a minus here. So Vx is equal to W into L, minus sign. So what is your shear force diagram? Shear force diagram will be, it is a UDL, so hence it is a inclined member. So it will be having WL, so with the negative sign. So this is a negative shear force diagram. So how to write that diagram? So you understand. So similarly, if you take what is a bending moment diagram? So what is the Mx? Mx is equal to, so you will be having the force. So negative again, W into X is the force acting at, if you take here, it is acting at its center of gravity at a distance x by 2 from the section considered. So you have to consider here at a distance x from the free end. So it will be Wx is the load acting at its centroid. That is centroid is equal to half of the length. So that will be your bending moment diagram. So W x square by 2. So what will happen at x is equal to 0. So your moment will be what is moment? Mx is equal to 0. So similarly at x is equal to L, mx is equal to so ml, you can say ml or mx is equal to W L square by 2. Okay. So how it will be now? Now the bending moment diagram will be, so it will be having the parabolic one. So it will be negative again. This will be negative. So that will be having, so W L square by 2. Okay. So that is the for the UDL. Now shall I consider? So this is the simple diagram for the cantilever one. So we will take another example of a cantilever again. So cantilever beam will be there. So sorry. So cantilever beam. So it will be subjected to a load at the end and again another load at this point. Then how it will be? So this also P load will be there and this also P load. So how it will be acting? What is the shear force? So shear force Vx, if you take and say this is the length A, this is length A, and total length will be, is equal to L. Total length is equal to L. So then what will happen? So up to here L. So shear force V. So at a section, so in between x varies from it is less than a and greater than 0. So that will be having the in this section. So Vx will be, so we have the Vx is equal to minus P. So okay, so up to here it will be same value, x is equal to variation. So if a value, take a x value, next another x value will be here. So x is greater than a and less than L. Then what will happen? So Vx will be, so Vx what will happen? Vx is equal to, so here at x is equal to 0, Vx is equal to minus P. At x is equal to A, also Vx is equal to minus P only. So when you say from here, so what is your shear force diagram? So minus P plus P it will be there. So Y plus P, so it will be acting from the section. Whatever acting downward, it will be negative, and acting upward will be positive. So your shear force will be, that will be 0 here. So what will happen to the moment diagram? So shear force, how it will look like? So you are having the shear force from here, it will be coming downward, and it will go up to here constant, and at this point it will go up, and the remaining length it will be 0. So shear force diagram looks like this way. So negative. So this is the only one line it will be there. That is a negative shear force diagram. So what will happen? Moment you will see. So mx is equal to. Similarly, you take the variation from x is equal to x from x is less than a and greater than 0. Mx is equal to what will happen? Minus p into x. So at x is equal to 0. At x is equal to 0, p is equal to moment mx is equal to 0, and x is equal to L, x is equal to 2, x is equal to 2 meter, or a meter, x is equal to a, mx is equal to p, mx is equal to minus p into a. Okay. So if you take the section, this is at the section, at the section say xx. So section say xx, this is say xx will be there, this is xx, and at section yy, that is if we take between, so at the section yy what will happen? That is that x will be greater than a and less than L. Then mx will what will happen? Mx is equal to minus, so your x measuring from the, so a value of x will be, for this one will be, this is the x value measuring from the pre-end. So for this one it will be measuring again from the pre-end. So this is the x. So minus p into x plus p into x minus a, it will be there. So simplify that one. So we'll be having p into a. So that means shear bending moment diagram. How it will be bending moment diagram? So if you see here, it will be 0 at this point, and it will be having a PA negative. So it will be coming this way, and it will be continuing constant here, PA. So okay, so this will be negative, PA will be there. So this is the bending moment diagram. Okay, so we will take another example. So example will have, so we take another example. So it will be having a beam. Sorry. So it will be cantilever beam. Similarly, when you take the cantilever beam, so it will be having the fixed support at this point, and it will be having the load of 7 kilonewton here, 7 kilonewton here. So at this point, another at a point 2 meter. So we have another. This is 2 meter. So total 5 meter. This is 3 meter will be there. So total from here to here 5 meter length. So this will be, what is this value? It will be 10 kilonewton, 10 kilonewton, and also it will be having another UDL over that one. So what is that value? So value will be 3 kilonewton, 3 kilonewton per meter. So what is the shear force? So you have to take the section at so take the section. So this is the section at this point. You take XX. First you take XX at a distance x from the free end. So at section XX. Okay. So what is the Vx is equal to? Vx is equal to, so we have one concentrated load. So that will be minus 7 minus what is that? 3 into x. So at a distance measuring from here, at a distance x from the free end. So that is the shear force. You'll be having that one. So at for the section, that is the x value. X value is greater than 0 and less than 2 meter. Okay. So that will be having, so Vx is equal to, at x is equal to, whatever x is equal to 0. So what is Vx? Vx is equal to minus 7. So okay. So at x is equal to 2 meter. So what is Vx? Vx is equal to minus 7 minus 3 into 2. 3 into 2. So that will be minus 13. Okay. Minus 13 kilonewton will be there. So what will happen here in the same value? So what is the moment at this point? So if we take the moment shall we take, or will take afterwards? So shall we take point Z, Vx is equal to, so we'll finish this also. Here the section Yy will take. So Yy at a distance x again, x from here to here. So take a distance x from here, Yy section. So we'll be having, we'll name this one. It's a distance x and all. So at Z shear force at this point, exactly at the 2 point, left side of this one. So left side of this nodal point, it will be having this one. So if we take the right side of this one, right side of this point, so say this is a point Z, right side of this one, and what is the shear force? Shear force will be, so we will calculate that one. So at Yy, at section Yy, so that will be having the x variation is the less than 5 meter and greater than 2 meter. So you will be having the Vx is equal to minus 7 minus 3 into 2 is a constant here. 3 into 2, 3 into x it will be there. So minus 10. So that value, whatever load here, it will be acting downward. So at x is equal to 2, what will happen? So Vx is equal to, so minus 7 minus 3 into 2 minus 10. So we'll be having minus 10 also. So totally, so you will get minus 23 kilonewton. So this is the value, and if you take so shear force diagram, so next what will happen? So we will calculate the bending moment for this also. Bending moment. So bending moment at mx is equal to, what is mx? for the first at YY XX will take at section XX. So take XX in the, so mx is equal to minus 7x, 7 into x distance, minus what is the 3 into x is the total load acting at its center of gravity at a distance x by 2. That's equal to, so we'll be having minus 7x minus 3x square, 3x square by 2 your value. So this is the value. So if we take at x is equal to 0, then mx is equal to 0. Okay, correct. And at x is equal to 2 meter, and then mx is equal to, so substitute value 7 minus 7 into 2 minus 3 into 2 square by 2. So you'll be having the value mx is equal to minus 20 kilonewton meter. So this is the range between from here to here you calculated. Then you will see, so we will see the moment calculation in between the value. So we at this point you noted down, this will be having the shear force. Shear force here is it will be having a shear force of 23 kilonewton at x is equal to 2 meter. So same if you take, so at x is equal to 5 meter, at x is equal to 5 meter at the fixed end, then what will happen? You will be having the Vx is equal to minus 7 minus 3 into 5 minus 10. So you will be having the moment is equal to minus 32, correct? Minus 32 will be there, 32 kilonewton. So moment calculation from here, you have to calculate, this is, you have seen the value for xx. Similarly, we'll take another slide. So we'll be having mx is equal to, so you take a section at yy, that is the value of a x greater than 2 meter and less than 5 meter. Then value of mx is equal to, mx will be, what is mx? Mx is equal to, so minus 7 into x, minus 7 into x will be there, minus 3x into x by 2 at a distance x by 2, minus 10 into x minus 2 it will be there. Okay, clear? So that will be say at x is equal to 2 meter, what your mx will be 2 meter length. mx is equal to substitute all the values here, you will get mx is equal to minus 20 kilonewton meter. Okay, so at x is equal to 5 meter, so we'll be having m is equal to minus 102.5 kilonewton per meter. So we'll write now what is the shear force and bending moment diagram. So this is your actual beam. So actual beam, what will we be having? So we will be having the actual beam like this. So it will be having the load of 7 ton here, 10 kilonewton here, and it will be fixed here, and having a UDL throughout the beam, and a shear force diagram. So it will be 7 at this point, 7 it will be there, and it will be 23 at this point, 23, and it will go 13, sorry, 13, and it will go up to 23. Then again it will be up to 32. So this is the shear force diagram for that one. So this is all pull negative bending moment, negative shear force. And if you see the bending moment diagram, so what will happen? Here 7 will be there, here 13. So here value this value 23, and here this value 32. So all are negative. Okay. So moment will be your moment diagram. So it will be having the because of both will be there, it will be having negative this way. Okay. So this is the value, you can get it here. That is 20 kilonewton will be there, and this will be having 102.5 negative kilonewton. Okay. So we'll go to next problem. So we'll see the how it will be shear force and bending moment diagram for simply supported beam subjected to point load as shown in the figure. So I could not do for the uniformly varying load. So I will take up in the next class. So now we will see for the simply supported beam. So for example, we will be having the simply supported beam with different loads like this. So we will be having one load here, two load, three load, all the three load will be there. How to what is the first step? You have to calculate the reaction first. So this is the beam, simply supported beam will be there. A and B, calculate the reactions. How to calculate the reactions? So this is the beam will be there. So you are using the sigma m is equal to 0 clockwise. So taking all the clockwise moment is positive. So what will happen? RB into 8. There is a 2, 3 plus 2 is so we'll be having RB into 8 meter, and so this distance 8 ton into 7 meter. 2 plus 2 plus 4, so 7 meter will be there. So another one 10 meter into 4 meter, 10 kilometer into 4 meter, 5 kilometer into 2 meter. So this has to be sigma m is equal to 0. So by solving that one, you will be getting RB is equal to 13.25. That will be acting vertically upward. So if you take the sigma Fy is equal to 0, then RA, reaction RA plus, so RA it will be there, plus 13.25, that is RB is equal to, that is total upward load is equal to total downward load. So 5, 10, 15, 8. So all the things, so RA is equal to 9.75 it will be coming. So okay. So this is clear how to calculate the reaction. So what you have to do, first you have to take the sigma m is equal to 0. That means whatever the clockwise moment is positive, taking that one. So take all the clockwise moment is equal to positive, and negative moment is equal to all the reaction. So all the vertical loads are there. You take all the things, moment and equal to 0. So you can, by solving that one, you will get RB is equal to 13.25. Then you will take sigma Fy is equal to 0. You will get this value. So RA will be getting. So once if you know RA and RB, then it's very simple to calculate what is the shear force diagram. So now you see here. So what I'm doing here, you take the section at a different levels. So this is a point you're interested. Take left side of that one, right side of that one. 2 points you will be taking 0, 0, 1, 1, and the point here. So 2, 2, 3, 3, 4, 4, 5, 5, like that. For every load point you will be taking. Okay. So only at the end. So you should not get any moment at 9, moment or shear force. So now we'll see what will happen. So shear force at 1, 1 denoted by V1, 1. Similarly, V2, 2, V3, 3 let be there. So take V0, 0. At this point, there is no load. acting. So all the shear force will be 0 here. So at 1, 1, what will happen? Only load acting here, only reaction. That is the reaction RA is equal to 9.75 Newton. So V11 is equal to 9.75 Newton will be there. So that is the here. Then up to come up to section 2.2, what will happen? There is no other load except this reaction. That means it will be constant from here to from here to here 2. You see that what is the section 2 also. So we'll be getting the same value. So it will be acting upward. Hence it will be positive. Okay. So 2 also will be getting 9.75. So if we take section 3, what will happen? So whatever the loads acting left side of this one. So whatever the loads are there, one reaction point is there, another one load acting on the beam will be there, 5 Newton. So now what will happen? So 9.75 minus 5 will be there. So that will be 4.75. So that means, so up to here, that will be their load, shear force will be 9.75. Then suddenly it will come down by 5 Newton. So that means it will go up to 4.75. Then what will happen? It will go up to here. It again it is constant. From 3 to 4 it will be constant. There is no other load. So hence there is no variation. So that we will be taking the constant from 3 to 4. Then again coming at this point, you will be having another load. So you will see that one. What will happen at 4 and 5. 4 will be same constant 4.75 and 5 it will not happen. So 5 becomes all the loads, summation of all the loads actually working upward is positive, downward will be negative. So adding that one, you'll be getting. So that means you already added here -5. So for that one, you'll be adding 10. So a new load has come, that is the 10. So you'll be getting negative of 5.25 Newton at this point, 5. Then again continue here, from here to here, it is constant again. From 5 to 6 is constant. So what will happen? So we'll see that. So 6, so it will again be minus 5.25 be there. So this minus 5.25. So then take the section at 7. So minus this minus will be there here. Minus of 5.25 minus 8. So that is the active load acting on there. So both will be coming 13.25. So then what will happen from here 7 to 8, it is constant again, and it has to minus will be there, minus the 13.25. Now the reaction you see here, it should be equal, otherwise something wrong. So whatever value reaction, it's equivalent to the summation of the loads acting on the beam, the reactions. So that means the shear force also, it has to join at the axis here. So here you got minus the 13.25. So 8 up to 8 also minus 13.5 will be there. When it comes to 9, it will be summation of both at this point. So it has to become 0 at this point. So no other. Okay. Now we will see how to draw that one. So this is your beam. So now you see that 9.75 will be there. It will be constantly going here and going by 5 down, and it will become 4.75. 4.75 it will go straight line. Then it will go down by 10. Then again 5.25 it will go to here. And so this is the diagram how to draw. So this is a positive, it will be there here, and negative shear force here. So we should take care of how it will looks like and all. Now hope it will be clear this one. Now we'll go how to draw bending moment diagram. So what will happen? Bending moment diagram. So this is the bending moment diagram MA, and we'll say denoted by MA and MB and so on. So we'll see MA. What will happen if your moment is what is moment? Load into distance. Whatever load acting either left side or right side, and the load into distance, perpendicular distance. That is the moment. So bending moment will be, so either you can take left side of the section or right side of the section. Now we are interested to calculate the moment at A. So A, what will happen? MA, either you can take right side, it should come 0. And also if nothing is there on left side, so hence it's 0 here. Okay. Then so MC, now once you come to MC, so what is the load acting left side of this one and the distance, perpendicular distance that one. So this is the reaction 9.75 into 2, that is the moment you are going to get here. That is 19.5. Then MD. So you can check either right side also, you should get the same value. MD, what will happen? This is the value. So this is the one value reaction is there and another load. So distance 2 into 2 plus 2, 4 it will be there. 5 into 2 meter. So that is the for the load. So you'll be getting 29 Newton meter. So that is a MD, it will be there. Then ME also you can calculate either right side, left side. You can right side if you see only one load is there, you can simplify that one. Instead of having all the calculation from the left side, you can go either right side or left side, but you should get the same value. See here 9.75 into 7 minus 3 into 5 into 3, this distance 5 meter and 10 into 3 meter. So this is the value you'll be getting. So for example, if you take the right side, 13.25 and only 1 meter is there. So this is the one. So you'll be getting the same value here. Okay. So again, it is positive. So all the it will going down and all. So now we'll see how to draw that one. So MB, so if you take all the things, it should be 0. So MB is equal to 0, it will be there. Okay. So take all the load from left side or right side. So here simply I'm telling, so MB is equal to, there is no other load acting right side of that one. So hence it will be so 29 it will be there. So since, so you might have seen in the shear force diagram, it's almost horizontal. So whereas in the concentrated load, it will be having inclined one. That means if you have the concentrated load in the beam, so you will be having the inclined line. Whereas for the shear force, horizontal line. So I'll show that one again. So you'll be having the inclined line here, like this. So if you see in the here, so it will be having only horizontal line. For the concentrated load, only horizontal line. Just remember, sometimes they will ask by giving the shear force, calculate the load. So that also reverse thing they may ask. So we should remember that. I will see that one. So this is the one. So I will take up, this is the one over. So this is the positive bending moment. So this is how to draw that one. So it will be having everywhere inclined lines. So we will see that one, how to calculate bending moment and shear force diagram for this cantilever beam. So now you might have seen this one, you have the UDL here for a length of 3 meter from the free end. Then you will be having the eccentric load at a, I think they have a bracket like this. They will be providing a load, inclined load. So now you should be very careful. So how to transfer this inclined load to exactly to our beam. So our beam always should be there, all the load, whatever load acting in the axis of x and y only. So we will be having this is y, this is X. So all the loads will be having this horizontal line. So you need to convert this inclined load to acting on the beam. So this is okay, it will be already there. So what will happen? How to convert this one? So you have the 40 kilonewton acting at a 30 degree. So you can take a horizontal component and vertical component. So both you can take this one. So that means 40 sin 30, sin 30 it will be there. And here 40 cos 30. So horizontal component and vertical component you can convert and put it on the value here. So once if you put, so this need to convert to this point. So this load will be coming here. So actually it will be same horizontal load. Once if you want to move to bottom, so horizontal load as well as some moment will be there. So due to this 40 cos 30 and this distance 0.7 meter, that will be acting here as a moment here. Okay. So moment acting. So this is converting horizontal load and a moment. So horizontal load equivalent to 40 cos 30. Okay. Then the moment will be that 40 cos 30 into the distance. What is the distance? 0.7 meter. So this value, that moment acting at this point. Now you converted only the horizontal load. Now you need to convert the vertical load also similar way. So vertical load you transfer here. So vertical load will be transferring it and it will be directly coming here down, and this is the acting in a clockwise direction. So 40 sin theta into 0.5. So that means this load will be directly coming as a vertical load, that is 40 sin 30. It will be acting vertically downward, and the moment 40 sin theta sin 30. So that will be acting in the reverse direction. So 40 sin 30 into 0.5 meter. So now you transferred all the loads. That means that horizontal load, component of this load, horizontal load, you transferred here and with a moment. And similarly, the vertical load and transferred here with a moment. So this point will be having one vertical load, one horizontal load, and two moments. So you can convert to one moment. So that means one will be acting anti-clockwise and one will be clockwise. So difference, if you take that one, you will get the moment acting in actually this one. So okay. Hope this is clear. Then I'll show that one how it will be. So what I'm doing here, so I'm converted into 40 cos 30, 40 sin 30 cos 30. So this is the distance, and so this is the value. So if we see this one, this to overall will be moving. So if you see in the previous one, this is the value 20 kilonewton vertically here, 20 into 0.5, it will be acting the moment at this point clockwise, and is 34.64 acting the moment at anti-clockwise direction at a distance 0.7. So whole thing, if you convert into totally, so that will be vertically load will be there 20 kilonewton, and this horizontal load 34.64, and the resultant moment will be 14.25 kilonewton. So this is the thing we need to do first. So now you have come to the normal cantilever beam. So we'll see that one, how to calculate the reactions. So sigma fx is equal to 0. So horizontal load, whatever load acting here, so horizontally, that horizontal, another equal and opposite horizontal force acting here, that is H is equal to 34.64, and fx is equal to 0, fy is equal to 0 take. That means all the three conditions, sigma v is equal to 0, sigma h is equal to 0, sigma m is equal to 0, all three conditions you are putting here. So this is sigma h is equal to 0, we got the horizontal force hd acting at this direction. Then sigma v is equal to 0, that is horizontal vertical forces. So that means 20 into 3 will be acting here, plus 20, that is 20 kilonewton here. So that will be equivalent to this whatever reaction required here. That is the VD. So HD will be here. So that then what will happen? Moment. What is the moment? Sigma m is equal to 0, md is equal to, how to calculate? This is the 20 into 3 acting at its centroid. So moment, you want to calculate the moment at this point. So this is the distance from here to here. So what is the distance? Here 1.5 meter is this length. This length plus 1 meter plus 1 meter. So 3.5 meter you are putting here. So the 20 into 3 is the total load acting at its centroid at a distance of 3.5 meter. And this is the 20 kilonewton acting at a distance of 1 meter. And the moment you see here 14.25, it's acting in the anti-clockwise direction. That also it's taking as the negative direction. So total moment will be minus. So it will be there. So that is 244 kilonewton meter. So okay, now we will calculate the reactions. Now we will see what is the shear force. So shear force, if we take at 1, so there is no other forces the left side of this section. So shear force will be 0. Then you take at 2, next you come to 2, what are the forces acting at left side, that one. So we'll be having the UDL. So it will be 20 into 3. That is a negative. It's acting from downwards. So that will be, that's why it's negative. Then if you come to 3 up to here, I think it is constant. From here to here, there is no other load. So it is same 60 kilonewton. It will be there, minus 60 kilonewton. And if you cross this one, so that value will be 4 will be minus 60 plus this minus 60 minus 20. This is also acting downward. So minus 80 will be coming here. So moment for the shear force, moment you need not to consider. Then if up to here you go 5. So same value will be there. That is 80. So whatever reaction you will be getting, it should be equivalent to this shear force. So once you put this minus, then you will be getting the positive here at the section of 6 if you take. That will be 0 you will be getting. So this is the condition you should get. Okay, this is the shear force. So it will be having the shear force 0 at this point, variation. So since it's a UDL, it will be inclined load will be there, inclined shear force, then it will be constant and downward, and again in constant and going upward. So that is the one. So then you will calculate the loading diagram. This is the one. So here, because of UDL only, so 0 to 60 it will be inclined. 60 to this 60 is a constant. There is no load, and it is coming down by 20 kilonewton, and again it's horizontal up to here, and 80 it is going up. Okay, so this is the shear force diagram. So whole thing it will be, because the cantilever beam it is acting downward. So if we cantilever, same cantilever, if you reverse, what will happen? Instead of having the support here, fixed support at this point, so if you put the simply supported fixed point in this point, then this will become positive. Shear force will become positive. Okay. So bending moment, how to calculate the bending moment, you will see. So we are interested to calculate the moment at A, B, MA, MB, MC, MD. Okay. So MA is equal to, there is no other load. So MA is equal to 0. So we have that one. So MB is equal to, so what is the, so we have the UDL 20 into 3. So at a distance, at centroid of this distance, it will be 1.5 of this distance. So it will be actually vertically downward for a distance of 1.5 meter. So that will be having a moment at MB is equal to, so 90 kilonewton meter will be there. And once we come to MC, what will happen? That is how to calculate the moment at this point means. So this is the UDL acting at its centroid only. So now you need to consider the distance from here to here, that here to here. So 1.5 plus another 1 meter. So 2.5 meter will be there. So that's what you see here. 20 into 3 and 2.5. That's why that centroid distance will be having that distance. So that is 150 kilonewton meter section before, and if you take section after, same thing. If you take section after, what will happen? So we will be having the another moment also here. So that will be coming to picture here, 14.25. So that also, so whatever you take here, So that will be this also from here. You have seen this one. It is acting anti-clockwise direction. This moment also acting anti-clockwise direction. So that's why you'll be having this also minus, this also minus. So totally minus 164.25. Now moment at MD, MD is equal to similarly, you see that one, the distance for the 20 into 3, 20 into 3, it's gradually increasing. There is a 1.5 of the MB, MC is equal to 2.5, and MD is equal to 3.5. The distance will be varying from here to here. Just see, you should remember that one, that the distance is changing from point to point. So distance from here it will be 1.5 will be there, from here to here 1.5 plus 1, another plus 1. So 3.5 will be there, and your constant moment it will be in the anti-clockwise direction. So that is the same 14.25. Then you have another constant load. So even then in the previous point, taking either left side or right side, only couple will come into picture, not the vertical load. Vertical load into distance, that is the same thing that should not consider for this point. So that's why we did not consider the vertical load moment. So zero distance. So whereas if you want to consider at MD point, that is 20 into 1 meter coming. So this is the moment at the MD, minus 244.25. So okay, so it will be having the whatever calculated in the previous, we will getting same value. So that will be check for you. So see the diagram, how it look like here. So you see the one, it is a UDL. Since UDL is a parabola will be there. From here to here is a constant, and there is a constant moment will be there. Moment is there. So it's having jerk here. So if we have the shear force constant, will be going in the shear force diagram. You might have seen that if you have the vertical load, it will go down. Similarly, if you have a moment, it will be going down, but by that amount. And again, it's constant. So you should remember in the shear force diagram, load is there means it will go in the same line. Similarly, moment is there means it will come down. Okay. So we'll have some problems related to gate. So this is the one frame ABCD is supported by a roller. So you see here is a roller is there, and it is at A, and also it's hinge at C, as shown in the figure. Now we need the loads are acting at a distance L by 2 P, and this also L by 2 P. And since it is having the roller, it can resist only vertical load to the perpendicular to the roller. Okay, so there is no, it cannot resist any horizontal load in the like this vertical load. Okay, if you have a horizontal load, it can react here. Now they are interested, the reaction at the roller end A is given by. So what is the reaction? So you'll be having P here, P is here. So what I told already, there is it's a vertical load acting here. If you have any horizontal load, then it would have resisted by this roller end here. Okay. So what is the value? Anybody can tell the reaction at the roller end? A will be, so value will be 0. So there is nothing here. So since there is no horizontal load, so that will be become 0. Okay. So we'll see some other problem. Consider the 3 prismatic beam with the clamped support. See, like this, clamped supports at PQR as shown in the figure. See, this is the figures PQR. So this is the clamped support, means again cantilever. So it will be fixed at the support here, and given that modulus of velocity E they are given, and the moment of inertia they are given, I is equal to given. The correct comparison of magnitude of shear force and bending moment diagram developed by at the support is. So what are the supports? So what they're giving? So why they're giving a E value and I value? I think they want to confuse you. So now you're interested only to write what is the shear force diagram and bending moment diagram. So they are giving these values, shear force diagram and moment. Okay. Now they given the formula here. So ABCD they given. Which one is matching? They have to see. For example, this is the one for the cantilever at 80 kilonewton, and shear force they given here. So constant shear force it will be there 80 newton, and this will be 20 into 8 meter. So it will be 160 here, and this, since it is a moment, so you know that one the moment it will not create any shear force in the any beam. So that's why it will be having the zero shear force. Okay, so if you have similarly, if you want to write the bending moment diagram, since it is a concentrated load, it will be constant here throughout here constant, whereas in the bending moment it is a inclined one. So if it is a UDL, it is inclined here, it will be comparable here. Okay, then shear force is constant here, moment will be shear force 0, moment will be m only, whatever value is there, 640 Newton. So what are the conditions you see here? So this P, Q, R are there. So P, so P is Q if you compare, Q is greater than P value, that is shear force, and it is not less than. So it is not matching. So this also not P is equal to SQ is not equal, and this one you see shear force at P shear force at Q is greater than shear force at P, and is greater than shear force at R. So this is matching. Whereas if become moment, yeah, MP, that is moment at P is equal to a moment at Q, moment at R. So the result will be your answer should give C value. So this is the one matching. So even this is not matching. Okay, this is not matching. This is not matching. So only thing you are matching. This is the one. So C is the answer. Okay. So here you see the beam having the double cantilever attached at the midspan as shown in the figure. The nature of force in the beam AB. So they want to know what is the nature of force. That means, as usual, I previously considered to how to convert all the things to the beam. If you see that one, how it will be acting at this point. So whether it will be all the length they are given, AC is equal to CB. That means the AC, that this distance equal to both are equal, and the CD is equal to CF. That also they are equal. So ED is equal to FG is all the things they are given. Now, what type of the nature of force in the beam? So they want to know whether it is bending and shear, or bending, shear and torsion, or pure bending or torsion. So if you convert, since all are equal, so it will be creating only the load and the moment only. So that means whatever they will be, if you convert all the things, what I told previously that have a bracket type similar to that one, if you move to the beam directly, so P into that distance will be there. All the things you can move here, and they will be having the only moment and force only be coming. So that will be having no torsion, no torsion will not come in a picture. So we'll be having only bending and shear. So this is the answer. So A will be said. Okay. So now you see the bending moment at the mid of the section. This is the one. So now the bending moment in kilonewton units at midspan location X. So they want to know what is the midspan location or bending moment in the beam with the overhangs. Hangs are there like this, overhanging here, and the support they are given here. So how to calculate bending moment at X? So what you have to do? So now you see that one, the answer they are given like this. How to calculate that one? We will see that one. So they are what they are given. So this is the one you can have 20 kilonewton will be there here, and 10 kilonewton will be there here, and this can be resolved into reaction. So what the spring will be having the RB reaction. Now we'll see how to do that one. Find the reactions at A and B, and find the bending moment at X. Okay. So reactions RA is equal to if you take this is as a beam, so you can calculate the values of RA, RB, and the bending moment at X. So that the answer answer C will be your answer. Okay. So we'll see this another one. So there is a portal frame shown in the figure, subjected to uniformly distributed vertical load W per unit length. The bending moment in the beam at the joint Q. So now you can see here, this is only hinged support will be there, here roller support is there. So now they want to know what is the moment creating for this UDL at Q. So anybody can tell this one. So it is similar to a simply supported beam. So what is the moment? It is can be considered as a fixed beam or a simply supported beam or how? So since there is no moment will be transferred from here to here because the hinge support is here. So moment will be 0 here. There is no other load acting on this column. So hence it will be having the 0 moment at this point. So that is the answer for you. So we'll stop another one problem. So it will be having the horizontal beam ABC loaded as shown in the figure. The distance of the point of counterfracture from A in meter is what is the value they are telling. So this is the beam they are given. So beam will be there at a distance of 0.75. This is 1 meter and having the load. All the things are given here, and whatever the cantilever portion is there. So whatever it is there, you have to convert into the load acting here plus that moment. So that's what you have done here. So that cantilever will be transferred to the vertical load and a moment for this distance. That means RP, the 10 kilonewton will be transferred here, and this value will be delta B is a compatibility condition you have to consider. So delta B is equal to 0 because there is a roller end and support here. There is a deflection will be 0. So this is the deflection. If we calculate that one, we will be having the value. So for the beam WLQ by 3I will be there, that is hinge support, and this will be having WL square by this load, and RB will be. So all the things if you have to take. So using this compatibility condition, you can calculate the value RB. So point of counterfracture, it will be at a distance 0.25 meter. So one more example I will take and I will stop by that. The bending moment diagram for the beam is given in the figure. The shear force is in the section AA and BB respectively are the magnitude. So you see here, this is the bending moment beam given in the figure. This is the bending moment diagram. So the shear force at sections AA and BB you need to calculate. So the moment is from here, the value is a constant here, and here to here it is inclining. So what will happen? The shear force will be, when moment is the constant, shear force what will happen? So we'll be having the value 1000 will be there. What value will be there for AB, AA and BB? So what will happen is, since the moment is constant, there is no shear force. So that will be 0 at this point. So that means the moment will be acting here. If you are acting moment only, so what will happen? There is no shear force. Only moment is there. That is 100 kilonewton meter. Only moment is there. So moment it will be coming constant up to this point, and from here to here it is inclined. So that means that inclined means it will be having the UDL type. So what is the value? So from here to here, if we take for a 2 meter length, 2 meter, that is 1 meter, 1 meter, 2 meter length. So it will be variation from 100 to 200 kilonewton will be changing. So for a 2 meter, it's a variation of 100. So for 1 meter, it will be having 50 here. So that is a value. C value is our answer. Okay. So we'll do one more problem, just the last one. We'll close by this one. So this is similar to that one. We have a group 1, group 2. So we'll be having the moment acting at the center point here, and we will be having the constant load and UDL and uniformly varying load. So now we have to match with this one. So if you have a moment at the center point, how it look like? So so what is the condition here? So you will be having the moment when constant moment is there, it will be dropping. The moment will be dropping like this. So maybe this is the condition. And if you have a constant load here, and it will be having the moment similar to this one. So UDL means UDL will be there. So what is the moment diagram? It will be a parabolic one. If it's have a uniformly distributed load, uniformly varying load, this is the your variation. So which one is matching? You just see that one. So for this one, it will be there here, and for this one here, and here, and this will be here. So which is matching? So if you see answer B. So for example, B is equal to, sorry, moment will be constant. So constant moment, this is the only thing. So B is equal to 4 will be there. B is equal to 4. So constant moment it will be there throughout. Okay. So 4, Q is equal to 4, okay, correct. And R is equal to 1, okay. S is equal to 3. Okay. Thank you. We'll meet again tomorrow next class. Thank you very much. We'll have a good day. So if you have any doubt, you can mail to us. We'll answer accordingly. Okay. Thank you very much.
Thank you very much, sir. I'm sure everyone here understood all the concept discussed thoroughly. So thank you one and all, and see you tomorrow for the gate training, the day 4, 2022. Thank you once again.
Thank you, sir. Okay, bye.